Okay, we have spring 2022 Chem 115 exam 1. I'm not going to keep flipping to it during the video. So if you want the answer key, it's right here. We're taking form 44. Okay, let's get into it. Octane is widely used in liquid form as greater efficiency fuels. Calculate the moles of octane present in 121 grams of octane using the correct number of sig figs. Okay, so the first step here, we're going to need to know the molecular weight. And let's get the right sig figs too. So they give us a periodic table somewhere down here. 12 has an AMU of 12.01, and hydrogen is 1.008. It's sideways, sorry. Okay, let's go back up here. Okay. So carbon was 12. It's supposed to be an arrow. Carbon's 12.01, and then hydrogen is 1.008. And in an octane molecule, we have 8 carbon atoms and then 18 hydrogen. So we can, where's my calculator? Here we go. Multiply those, get 96.08, and then 18.114. Okay, and then we can add those up. Okay, add those up. 114.224 grams per mole. Okay. Now they want sig figs, and the molecular weight of carbon was only down to 2 decimal places. So this one goes away. Okay. Okay, and we have 121 grams of it. So, and also this is only to 3 sig figs, so we're also gonna go down less. But 121 grams times 1 over 114.22 grams, and then 1 mole. Grams cancel. 121 divided by what we just calculated. It's just over 1. Okay. And let's see. Okay, so now it becomes a sig fig issue. Obviously, these are wrong. And we did multiplication, so we're just going to go down to the lowest number of sig figs. So in that last step, this number has 3 sig figs. This number has 5. So just round down to 3 sig figs. And this is going to become 1, oh god, that's a 0, 1.06 grams. So we're going to pick B, which is correct. Excellente. All right. The following balanced equation describes the combustion of ethane. How many grams of carbon dioxide are produced if 29.4 grams of ethane and 95.3 grams of oxygen are used for this reaction? Okay, limiting reaction problem, or limiting reagent. So first we got to figure out what the limiting reagent is. So, and they want how many grams of carbon dioxide are produced. So let's just figure out which reagent makes less carbon dioxide. That's our limiting reagent, and then that's just going to be how much carbon dioxide we form. So once again, we're going to need the molecular weights, and I'm not going to be concerned about sig figs. Also, here I'm going to completely ignore sig figs, because if we look at the answers, I don't know why I circled those. Look at the answers. None of them are really close. So we're in the last problem. We ran into like this issue where we had 2 answers that are like right-ish. Here, well, maybe these 2. Here, I have a hunch that's not going to be the case. So I'm going to be less anal about the sig figs. So, okay. We know, let's get the molecular weights of our reagents. Carbon is 12.01. Hydrogen is 1.008. Oxygen is 15.99. Okay, and then for ethane, oh shoot, we're gonna have 2 times 12.01 plus 4 times 1.008. Oh god, run out of room. Okay, which is 28.052, and then let's see. Oh yeah, oxygen, which is just what's this is grams per mole. The O2 is just going to be 15.99 times 2, so 31.98 grams per mole. Okay. Now, they give us grams of how much each are reacting. So let's figure out how many moles we're going to have. So we have 29.4 grams of ethane. I'm going to say E times, and then we have 1 mole per 28.052 grams. And that's ethane. Okay. 29.4 divided by that molecular weight gives us just over 1.048. Just over 1 mole of ethane. I'm shorthanding that E, I'm just saying that's ethane. I don't want to write out the whole thing. Okay. I'm going to erase now to give me some more space. I'm going to erase this. Okay, let's figure out how much oxygen we have. We have 95.3 grams, and we know the molecular weight. In 1 mole of O2, there's 31.98 grams. Erase this. We have, oops. Okay, reacting, we have just under 3. Oh, oops. Just under 3. I'm gonna round that up. Moles of O2. Okay. So, let's see. Okay, and get rid of this too. So these are how much moles we have reacting. So looking at it, ethane reacts, it has a stoichiometric ratio of 1, and oxygen has 3. So I know my limiting reagent is going to be oxygen because it's being used up in 3 moles per the 1 reaction, and ethane's being used up at 1/3 the rate. Okay, so now if I know oxygen is my limiting reagent, we can do 2.980 moles O2. Let's get our dimensional analysis line. And we're looking for grams of carbon dioxide are produced. And in 3 moles of O2 reacting, we're going to form 2 moles of CO2. I got this from that number right there. And in 1 mole of CO2, there are how many grams? Let's see. CO2 molecular weight is 1 times 12.01 plus 2 times 15.99. Okay, it's about 44 grams per mole. So let me throw in this ratio. Okay, so according to our dimensional analysis here, moles of O2 cancel, moles of CO2 cancel, and then we would just have grams of CO2. So now multiply the top, divide by the bottom. 2.98 times 2 times 43.99 divided by 3 divided by 1. Okay. And that gives me 87.39 grams of CO2, which is E, which is correct. Okay. Identify the proper isotope and element X represented in the nuclear fission reaction equation shown below. So we can balance, let's go to green. We can balance these nuclear reactions in the same way we balance chemical reactions. We know that these top have to equal, the mass numbers have to equal on the left-hand side of the equation to the right-hand side of the equation. Same deal for the bottom. So let's do the top first. 235 plus 1 equals A plus 141, it's an A, plus 3 times 1. So, let's do this. A equals 236 minus 141 minus 3. So A equals 92. If we look at our answers, so we know this top number has to be 92, so it's definitely not A, it's definitely not D, and it's definitely not E. We still got to do the bottom row, though, to get the next number. Okay, so let's use orange. Why not? Let's do the exact same process for this bottom row now. 92 plus 0 equals Z plus 56 plus 3 times 0. So that's just 0. So is this. So Z is just 92 minus 56. Z equals 36. So, oh. Okay, just kidding. We actually didn't need to do the bottom row because now I notice the atomic number is actually the same for both. So now, I guess now what they're just testing here is, do you know what the atomic number is? The atomic number, this bottom number right here, is how many protons are in your element. So we just need to go look at the periodic table to see what corresponds to 36 protons. So if you can turn your head for a second, 36 is Kr, which I'm pretty sure is krypton. So that would leave us with B, which is correct. Excellente. All right. Selenium is used to make pigments for ceramics, paint, and plastics. It is also useful in photocells, solar cells, and photocopiers. What type of decay would a mass number 72, atomic number 34, selenium nuclide undergo? Band of stability provided. Okay, so let me just remember these. We're going to need the band of stability for this one. Did I? Okay, I did not put it here. We have mass number 72, atomic number 34. So how many neutrons do we have? We have 72 minus 34 neutrons. So I know I have 38 neutrons. Reason being the mass number, this top number is neutrons plus protons. The bottom number is just protons. So if you take the mass number minus the atomic number, you get the number of neutrons you have. So let's go down to our band of stability. And actually, hold on. How many protons do we have? Let me try to remember. All right, we have 34 protons, 38 neutrons. Let's take a gander at the band of stability. We're plotting protons versus neutrons, and we have 34 protons, so somewhere like this, and 38 neutrons, so somewhere over here. Okay. Wow, we are pretty close to the line. So if we remember, for our nuclear chemistry, anything up in this region will do alpha decay if it has just straight up too many protons. If it was above 83 protons, it would do alpha decay. We're nowhere near there, obviously. So we're going to be one of the beta decay regimes. If we were above this line in this direction, we would do electron emission or positron capture. This would be beta decay. And if we're down here, whoa, that was terrible. Arrow. If we're down here, we will do electron capture or positron emission. Okay, let's see where we're at. Okay, A. That's pretty much what I just said. So there we go, A, which is correct. Okay. Which of the following atoms has a different number of neutrons? As we somewhat just did in the last question, we know that this top number is the mass number, which equals protons plus neutrons. The lower number is the atomic number, which is just protons. So if you take the top number and minus the bottom number, you know how many neutrons you have. So let's go through each one of these examples and find out how much neutrons they have. This top one, for whatever element RH is 103 minus 45. That's 58. This top one has 58 neutrons. The next one, B, has 104 minus 46. Also 58. 105 minus 47. Also 58. Looking good. 102 minus 44. 58 again. I have a hunch this one's not going to be 58. But what do I know? 60. Okay. Which of them has a different number of neutrons? Those all look the same to me. E is our choice. And let's see, what is this? 5? E. Correct. All right. Number of boron atoms in a point that many grams of uranium borohydride. Okay. So in 1 mole of sodium borohydride, we have 4 moles of boron. Not sodium borohydride, uranium borohydride. Let's see. Okay, in 1 mole of this species, we have 4 moles boron. Okay. And I know that because there's 4 of these groups. You know, there's a 4 right here. Okay. Let's first get the molecular weight of uranium borohydride to figure out how many moles we have. Then once we have the number of moles of the whole species, we can do this conversion, and then we can use Avogadro's number to go from moles of boron into atoms of boron. So first, let's get the molecular weight of this. And I definitely do not know the molecular weight of uranium off the top of my head, or boron, for that matter. Okay. You're going to have to turn your head sideways again. I don't even know where uranium is. Somewhere near the bottom, because it's nuclear reactive. Is it U? I think it's U, right? Okay. Uranium is 238 on the dot, and then boron is 10.81. Uranium was 238.0 grams per mole. Boron was 10.81. Okay, and then hydrogen is 1.008 grams per mole. Okay. What is the molecular weight of 1 mole of uranium borohydride? We're going to have 1 uranium atom, 4 of these, and then 16 hydrogens. Take those and add, okay, what does that equal? 238, 10.81 times 4, 43.24 times 1, okay, 16.128. Add these up. Okay. I'm going to erase this now. In 1 mole of uranium borohydride, we have 297.368 grams in 1 mole. Okay. And we know we have this, maybe I should change colors. We have this many grams of it. So let's flip this, do a little unit conversion real quick. 0.302 grams. Grams cancel. Okay, this is how many moles we have. Oh, wait, oops, I did that wrong. Okay, 0.302 divided by 297. We have 0.001016-ish moles of uranium borohydride. Okay. Now, okay, this is how many moles of the whole species we have. Let's set up a line like this, make it a little cleaner. And this is the uranium borohydride. And in 1 mole of uranium borohydride, you have 4 moles of boron atoms. And in 1 mole of boron atoms, you have Avogadro. In 1 mole of boron, you have Avogadro's number worth of atoms. And I think that's Avogadro's number. Let me just double check. Yeah. So Avogadro's number is number of atoms in 1 mole. So that's how we're going to go from moles to atoms. Throw this all in our calculator. Multiply all the top, divide by the bottom. 0.001016 times 4 times 6.002 times 10 to the 23rd. Divided by 1, divided by 1. Okay. We get 2.446 times 10 to the 21st atoms of boron, which corresponds to C. And it's C. Wonderful. Okay. What are the coefficients in the following unbalanced chemical equation shown below? Balance this chemical reaction, essentially. Okay. Let's start with the elements that are less available, and then do the... You should balance hydrogen last, because it's in nearly every species, and especially it has an elemental form, so it'll be the easiest to balance. Save hydrogen for last. Do the ones that are less apparent in the species first. So I'm going to assign this a 1 and this a 1. Nitrogen's balanced now, so I have 1 nitrogen on each side. And if I have 1 boron there, I'm going to have 1 here. Let's do oxygen next. So on the right-hand side, I have 4 oxygens, so I'm going to want 4 here. And let's see. Okay, now the left-hand side has all the hydrogens. Let's see where we're at. This is 6 H's. This is 8 H. So on the left-hand side, we have 14 H's. This is 4. This is also 4. So to get to 14, we need 10, which is 5. So does that look good? Wait. Wait, why are there... Wait, this should be 6. Hold on. This should be 3. 3 because we want 6 H's. Okay. So we have 14 H's over here. We have 14 H's over here. 1 nitrogen on each side. 1 boron on each side. 4 oxygen on each sides. Yeah. So what answer choice does that leave us with? Looks like B. Okay. the general strategy whenever you're balancing equations is pick the less abundant elements first. The reason I balanced nitrogen first and boron first is because they appear in their species only in like one, so they're easier to balance. When I see stuff like hydrogen that's in every single species, I leave it for last, especially considering this, because I could just put whatever number I want here to balance out my system. Just a tip. Okay, so 7b. 8. Which of the following is the correct formula for zinc hydroxide? So we know zinc is a metal, and then hydroxide is OH, which O and H are both nonmetals. And when you form a bond between a metal and a nonmetal, you're going to get an ionic bond. So we know that hydroxide is going to steal electrons from the zinc, and then the resulting ion cores are going to be held together, which sounds a little confusing, but all we need to do is match the charges. So we know zinc always has one oxidation state of 2+, and we have, oops, I already wrote on it. We have this table over here. I found this, it just lists some of the common oxidation states. Ones that are worth noting, so zinc always is going to have a +2 oxidation state. Same with nickel, and then titanium and scandium also only have one oxidation state. So they could ask you really this same question with any of these like 4, and you would perhaps be expected to know these elements that only have one oxidation state. Because if they ask you the same question with iron, you would have to know, they would have to tell you if it's iron 2+ or iron 3+. So perhaps try to remember these 4 elements that only have the one oxidation states. But we know zinc has 2+. So what does that tell us? So when we're forming these ionic bonds, the charges need to cancel because zinc hydroxide is going to be a net neutral atom. And hydroxide is OH. Oxygen has 6 valence electrons. Hydrogen has 1. These are going to form one covalent bond right there. And then in an ionic bond, this oxygen is going to steal one more electron from the metal to fill that electron right there and then get its 8 valence electrons. So this essentially has like a -1 charge. So in order to cancel them out, cancel out the 2+, we're going to need 2 hydroxides. Okay, so that leaves us with C. So with these problems, you're really just trying to balance the charge. Zinc, we know, is 2+, and hydroxide is going to have -1 or 1-, whatever. So we know we're going to have 2 hydroxides in order to make a neutral atom. 9. In a lab, a student used a volumetric pipette to measure 10 milliliters of water at 20 degrees Celsius into a pre-weighted Erlenmeyer flask and recorded the data below. If the theoretical density of water at 20 C is that, calculate the percent air for the experimental density. Experimental error, we know, let me write on the left here, is going to be expected. Oh, this might not fit. Expected minus measured over expected times 100. I'm shorthanding expected into EX. Okay, that's how we're going to get percent error. So we need to get what the measured density was, because the theoretical density is going to be our expected. So we just need to figure out what the measured was. They took our volume's 10 milliliters. Okay, wait, what are we doing here? 10 milliliters of volume, and then, okay. The flask weighs that, and when we weighed the total, so the empty flask weighs that much, 86.99, the flask plus whatever water was in it was 96.89. If you subtract the total minus the weight of the flask, you get how much water you had. 96.89 minus 86.99. The water mass is 9.9 grams of H2O. And we know the volume is 10 milliliters. So if we want density, and the units of density are grams per milliliter, and I expect that's what they give us right here too. So we can just take our grams and divide it by the volume to get the density. So 9.9 divided by 10.0. So our density is 0.99 grams per milliliter of H2O. Okay, that is our measured. So now let me erase this mess. The expected was this value. This is our measured. So let's do that. 0.998202 minus 0.99 all over 0.998202 times 100. Okay, let's put that in our calculator. And I got 0.8216% error, which is E, which is correct. Wonderful. Okay, problem 10. A 50 milliliter graduated cylinder contains 25.1 milliliters of water. A 145.8820 gram piece of osmium is placed in the graduated cylinder, and the water level rises to that number. What is the density of the piece of osmium? So, when we add so what's happening here? We have a cylinder before. Oh, I should not have made it blue. Okay, we can just do this. Red cylinder. Nice. Okay. It's nearly halfway full with water before, and then we put in our piece of osmium, and it raises like that amount. What is this change in volume? Well, we know before it is 25.1 milliliters of water, and finally it has 31.6 milliliters. So our change in volume, why did I do equals, is 31.6 minus 25.1 milliliters. So it changes that much volume. And that change in volume is how much the osmium, how big it is, how much space it takes up, because it's being completely submerged in the water. So by how much volume's added into the fluid is the volume of our chunk. So we now know the volume of it, and they also tell us how much it weighs in grams. So we know the grams of it, we know the milliliters of it. Our answer wants it in grams per milliliter. So just take our mass and divide it by the volume. .443 grams per milliliter. Okay, and that leaves us with answer choice D, which is correct. A mixture of 0.15 moles of hydrogen gas and 0.125 moles of oxygen gas is contained in a vessel with a volume of 40 milliliters. If the atmospheric temperature is 298 Kelvin, what is the total pressure in the balloon? Okay, so sounds like we have a a balloon that is also being referred to as a vessel. Got some oxygen. I don't know why I'm drawing a picture. Some hydrogen. We're probably going to need ideal gas law here. So they give us moles of this, moles of this. So moles is good. They give us a volume. Volume's good. They give us a temperature. R is a constant we can get from the bottom of this exam. They want the pressure in the balloon, so we can just solve for that. One equation, one unknown. So let's go get our R constant first. So let's see here. Is there only one? Well, we'll see what they give us. Okay. Bottom of the exam, fun place to be. It's the equation I'm using. Ideal gas law. Wait, okay, where is it? Okay, here we go. Oof. Okay, that's in liters, which, oh wait, we were in milliliters, weren't we? Okay, that's not an issue. Okay. Type that in my calculator somewhere. 0.08206. And that's liters times atmosphere over mole Kelvin. Let's go back up here. On the right, on the left. R equals 0.08206. And that was liters times atmosphere. Wait, what was it? Liters atmosphere mole Kelvin. Okay. Getting the units right is very important. Okay. So let me get rid of my very great picture. Okay. There's, in theory, two ways we could solve this. We could solve for the partial pressure of each species and then add them. So actually, maybe I shouldn't have erased my picture. So each one of these species is contributing a partial pressure to the system. We could do essentially like 1 and 2 ideal gas laws, one for each species, and then add them up. Or it is exactly the same if we just do this instead. If we do like number of moles of O2 plus number of moles of H2, it's going to come out to be exactly the same because none of the other variables are changing. Boom, boom, boom. Okay. Oh, shoot. All right, let's calculate pressure. So let me solve for pressure first. Also, okay, let's start plugging stuff in. P equals number of moles of O2, 0.1250, plus moles of hydrogen gas, 0.15, times R, but so those are moles. Let's change our R constant a little bit. Let's change our R constant into, move me up again. Let's change our R constant into milliliters. So the main thing I'm seeing here is this is in liters. God, it keeps doing that. This is in milliliters. So how could we get our R constant into milliliters? Well, we can times it by 1,000. This is like liters, and in 1 liter, there is 1,000 milliliters. So you can just times it by 1,000, and then you get R equals 82.06, and that's in the units of that are milliliters times, oh god, I'm running out of room. Milliliters, atmosphere, and then mole Kelvin on the bottom. Okay, you're gonna have to forgive me for what I just wrote. Okay, there's our R constant, which now is in the right units. Okay, let's put that in. 82.06 divided by, let's see, divided by the volume, which is 40 milliliters, and also we need to times by T. Give me some more space. Okay, times by T, which is 298. And let me get rid of this. Okay, the units check out. Okay, let's do this math. 0.125 plus 0.15 times 82.06 times 298 divided by 40, 168. 168.12, which, let's see, this was in our units of pressure is atmospheres. So that is answer choice A, which is correct. Problem 12. The transmutation from mass number 238 uranium into 239, whatever NP is, happens through which series of decay processes? Okay. Let's look at our answer choices first. So all of them start with neutron capture, other than C. Okay, and also what do we want? What do we want to happen? From the whole step, we want our mass number to increase by 1 position. And the problem I see with C right away is that you capture an electron, which has a mass number of 0, and then you emit a beta, you do a beta emission, which also has a mass number of 0. So the answer choice C will not work because it's not going to change your mass number. So C is wrong. We're going to take that one right off the table. The other 4 all start with neutron capture. So we know that's going to be our first step. So let's see what that looks like. So we have our 238 uranium, and we are capturing a neutron. So we are left with uranium-239. So then this is going to be our starting point for the next step. And we want, for our final product, we want NP239. So that's an uppercase P. Oops. Okay. So how do we go from uranium-239 to NP239? Our mass number is going to stay the same. So we don't want any mass number changes, but our atomic number goes up by 1. So what we need to do is turn a neutron into a proton. Okay. So let's balance this. You know we're gonna have 0, and then we're gonna want -1. So we're gonna do beta emission. And I figured out I just balanced our products here, and we're going to get that beta particle. So we're going to have a beta emission, which we also know changes a neutron into a proton. Beautiful box. So therefore, B is our right choice, 12B. Sally is preparing for a hot dog eating contest. Yesterday, oh my God. Yesterday, she ate 29 pounds of hot dogs in 10 minutes. How much hot dog in grams did she consume per second? Okay, great chemistry question here. So this one obviously is just straight up, do you know how to deal with units? And let's see if we do. Okay, so they want grams per second. So she ate, let's see what our starting point is here. She ate 29 pounds in 10 minutes. Okay, let's just straight up do dimensional analysis all the way to the final answer. Okay, we want grams per second. So let's convert pounds into grams. I have not the slightest clue. Actually, I think I do. I think it's like 450 grams per pound. There's no. Oh yeah, there we go. Oh my God, look at that. Nice. Okay, 453. Let me. Can't remember 6 digits. Okay. So I have 453.592 grams in 1 pound. In 1 pound, I have 453.592 grams. There, my pounds would cancel. Wow, red on orange looks bad. Okay, anyways, too late now. Okay, my pounds would cancel. Now I have grams per minute. Let's get minutes into seconds. Well, I know in 1 minute, I'm going to put minutes on the top so that those cancel. Minutes cancel with minutes. And now the only units I have left is grams and then seconds. Sick. Didn't even need all this space. Okay, let's see what we get. Multiply all the top, divide by the bottom. 29 times 453.592 divided by 10 divided by 60. 21.924 grams per second. Do sig figs matter? No. There's only one answer choice that's even close. B. Well, sig figs matter, but sig figs don't matter on this exam problem. So therefore we don't care. B is the only answer choice that's close. 13B. Wonderful. 14. A 514.0 gram block of aluminum cools from that temperature to that lower temperature. What is the energy change associated with this temperature change from the standpoint of the block? The block is our system. You know, that's that statement right there. Block equals system. And I can tell you, look at this. Look at these animals. Look at the signs. That's what's going to matter. We're gonna get this choice or we're gonna get this choice, and you need to pick the signs. I can tell you right now. All right. Anyways, the block is our system from the standpoint of the block of aluminum. The specific heat is that number. Thermochem, we have a temperature change of a material. Also, they're giving us a specific heat. We need to know this equation. Q equals MC delta T. And I'm pretty sure that's actually not included on the equation sheet. No. Okay, you need to know that one. Q equals MC delta T. Okay. Let's plug in our stuff. Q is heat. M, we have 514 grams. That's mass. C is the specific heat, which is 0.9 joules per gram per Kelvin. And then we have change in temperature. Delta T equals T final minus T initial. Anytime you take like a delta, you're always going to do your final minus your initial. 365 minus, I should probably write this. 365 minus 298, that's going to give us 67. Change in temperature is 67 degrees Kelvin. Okay. Let's see what we got here. Grams cancel. Degrees Kelvin cancel. And then we will just have joules. So 514 times 0.9 times 67. I get 30,994.2 joules. All the answers are in kilojoules. So I'm just going to divide by 1,000. So there is 1 joule in... Wait, no. There is 1,000 joules in 1 kilojoule. So I'm going to divide that by 1,000. 30.9942 kilojoules. Okay, so it's not any of these. We need to figure out, is it positive or is it negative? What is the energy change? Okay. Hold on. We have our block of aluminum. What is the energy change associated with it from the standpoint of the block? So the block is our system. Is it gaining energy or is it losing energy? It's cooling down. The temperature is decreasing. So it is losing energy to the, man, red on orange again. Okay, it is losing energy to the surroundings. Our system is giving off heat to the surroundings. It's losing energy. The change in energy of our system is negative. The energy is decreasing because our system, the block, is losing kinetic energy. Its temperature is decreasing. 14B. Okay, 15. Man, let me erase this. That looks bad. Okay, 15. A system does blank kilojoules of work and gains other kilojoules of heat from the surroundings. What is the change in internal energy of the system? Okay, another thermochem question. Do we know system and surroundings? Okay. Oh gosh. Why does it do that? Okay. Block of aluminum. This is our system. Okay. It's doing 753 kilojoules of work on the surroundings. It's losing 753 kilojoules, and it's gaining 516 kilojoules of heat from the surroundings. And the internal energy is of our system, so I just care what's in here. So what's the change here? Let's do in energy minus out. Very rigorous. 516 is coming in, 753 is going out. Negative 237. Which 15A. Wonderful. Okay. So if you would have gotten this one wrong, you probably would have picked B. You need to be tipped off by some of the keywords here. Our system is doing work. So energy, it's doing work on the surroundings. So therefore I know it's leaving. And here with the heat transfer, they explicitly say gaining energy. So we know that one's going to be positive. So here you kind of just got to be tipped off by the wording of the sentence to figure out what's coming in, what's leaving, what's positive, what's negative. So for 15, we get A. 16. For the following reactions at constant pressure, determine in which reaction no work is performed on or by the system. Okay. So, thermochem again, we know that PV work exists. When you have a change in volume, whether increase or decrease, you can get a resultant work and change in energy. And when pressure is held constant, volume will change as a function of how many moles are in your system. So let's say we have this vessel of reactants and this vessel of product. If we don't actually, I have a better idea. Say I have a balloon where it can expand, and as you fill up a balloon, it can expand or it can contract as you let air in or out. It's at constant pressure. So if during our reaction we're adding number of moles via reaction, it will expand. Our balloon could expand to a bigger size, and then we're consequently going to increase this volume, and we're going to do PV work, which is what we don't want. We want a condition in which no work is performed. So we want the same size vessel, same size balloon. So how do we get a situation where we have the same amount of gas before and after? Well, we look at the stoichiometric ratios. So, because we know reactions proceed always in stoichiometric ratios. In A, we have 3 moles of gas forming 3 moles of gas. So that one's probably our right answer. Let's keep going through the rest just to see. In situation B, we have 3 moles of gas again, but here it's forming 2. So in situation B, if we're at a constant pressure, our balloon is going to get smaller, and we would have a negative delta V. Also, well, you could care about the sign convention. Doesn't matter for this, but so we would have a change in energy there and it'll work. For condition C, we have 2 moles changing into 4 moles, so that one would expand and we'd have energy change there and to work. For condition C, we have 2 moles going into 1, and here I'm just adding the stoichiometric ratios in case it's not apparent. And then in E, the last condition, we have 3 plus 1, we have 4 moles turning into 2, so we're going to contract there. The only condition in which we have the same number of moles before the reaction and after the reaction is A. Therefore, A is going to have the same volume as before as it does after. Same size balloon, no PV work done. 16A. Yeah, okay. 17. Acetone, the solvent in many nail polish removers, has a density of that number. Calculate the volume in milliliters of 37.2 grams of acetone. Okay. Unit conversion problem. We have 37.2 grams of acetone. I'll write it out. And we know that there are 7.791 grams in 1 milliliter of, I'm actually going to get rid of this, of acetone. Okay. So we have these two things. If I want the units to cancel out and get me just milliliters, I need to flip my conversion here. So let's do 1 milliliter on top, 0.791 grams on the bottom. Goodbye. Let's multiply these two. Grams cancels with grams, and we get, let's take 37.2 and divide it by 0.791. You get 47.029 milliliters. And sig figs might be an issue here, but B is the only answer choice that is close. B. 18. Iron 59 with a half-life of 44 days is used to study iron metabolism in the spleen. How many days would it take for 28 grams to decay to 7.5 grams? I don't remember the exact equations off the top of my head. No worries, because they luckily give them to us right here. So for half-life decay problems, these are the 2 set of equations we're going to need. So let's write those down. Where are we at? 18. Okay. So we got, where are we at? 18? Okay. 18. We got the natural log of the final amount over the initial amount. N is going to be how many grams we have at the end. N naught, or N0, is the grams we have initially, is equal to negative K. K is the rate constant, which we're going to have to calculate, times the amount of time it's going for. And they want how many days. So this T, I already know, is actually what we're going to be solving for. So we're going to solve this one second. And then we have the other equation, which is the rate constant, K, times the half-life equals the natural log of 2. Okay. So, okay. Let's see here. We know we're going to solve this one first, and then we're probably going to take our K that we solve for, put it into this equation, and then we will be able to solve equation 2. So, let's see here. Let me switch over to blue. So, K is unknown. K is our initial unknown, times the half-life, which is 44, let's keep track of units too, days, equals the natural log of 2. So K equals the natural log of 2 divided by 44. Okay. So there we go. Now we have K. This equation can go away. Let's solve 2 now. The natural log, what is N? N in the numerator is our final number of grams, 7.5, over the initial number, 28, equals negative, let's put this in parentheses, 0.0157, that's what we calculated earlier, times the number of time it takes, which is what we're solving for. So let's take the natural log of 7.5 divided by 28, and then I'm going to divide over, negative k. And that gives me a t of, lowercase t, of 83.62. And that gives us answer choice B. Yeah, you couldn't really go wrong with sig figs here anyways. So answer choice B, and I lost my answer key. 18B. 19. Which of the following nuclides is stable? First thing, anything with a number of protons greater than 83 will undergo. So protons greater than 83, you will undergo alpha decay. And wow, none of them have more than 83 protons. How wonderful. Also, I put the band of stability here. Nice. Okay. Anyways, so all we need to do here in this problem is see which of these elements lands on the band of stability, because as the name implies, the band of stability is where elements are stable. So we got this one. Let's to make this go quick, let's figure out how many neutrons are in each one first. Mass number minus atomic number gives you neutrons. This one is 28. This one is 29. This one is 8. This one is 66. This one has 14. Okay, let's start with our first one. We're going to plot 16 protons versus 28 neutrons. 16. No, this is let's make this a little smaller. So I'm going to plot answer choice A, which is 16 protons to 28 neutrons. 16-ish. That's all the way up here. So this is answer choice A, and that is far-ish away from the line of stability, so no. Okay, next choice. 19 protons, 29 neutrons. Doesn't sound very stable to me. Let's check anyways. Same deal. Answer choice B is right there, kind of far above. No. 8 and 8. Okay, I should have made this one bigger. Okay, 8. Okay, that doesn't look bad. Also, I have a hunch this is going to be the answer choice. If you know the atomic mass of oxygen, it's 15.99. The most stable isotope of oxygen is oxygen 16. So this one is definitely the right answer, but let's check the other two. Okay, let's check the other two. D, we're going to plot 46 to 66. 46, 66 looks a little bit high. Looks a little bit above. It's pretty close though. D doesn't look terrible. E, we got 18 to 14. That looks a little bit below. That would be like right here. A little bit below. Also, it's kind of hard to see the trends I'm drawing. But if you used the full scale one at the bottom, it might be a little more obvious. 19, answer choice C. 20. Calculate the delta H for the reaction of that reaction given the following reactions. Okay, so this relies on the knowledge that you can add together reactions to get the desired reaction, and when you do that, you can do the same thing with their delta H's. So the first step is going to be yielding this reaction. So we want this solid calcium, what is that? Calcium carbon trioxide as our product. So let's flip this reaction. I'm going to flip it. Let's do CO2. I'm not going to write the phase, plus calcium oxide turns into this thing. And then I'm going to flip my delta H. So all I did there was reverse the direction of the reaction and then flip the delta H. So this is now no longer useful to us. Let's use this instead. Now we can combine this first reaction with this reaction to yield the desired reaction. So let's do that. If we just straight up add them, we will get this reaction. If we have this calcium oxide on the left side and then a calcium oxide on the right side, they will cancel. And then as you can see, there's no calcium oxide in this desired reaction. So if we add them together, I'm going to get this calcium plus, I'm just adding together the reagents of that first equation plus the reagents of the second equation. And then now we're on to products. And we can now add together their delta H's. So we're going to take negative 635.1 and add on 178.3. Wait, that should be negative 635.1 minus 178.3, negative 813.4. Okay, which leaves us with answer choice D. Yeah, and also these went away because they're on both sides. They could modify this reaction if perhaps they weren't in perfect ratios. So here, I just added the equations directly, but perhaps you could have done one equation 1 plus 2 equation 2s. So if this was perhaps something like 2 CO2 and then 2 CO3, maybe I would have had to multiply this by 2. That example might be on another exam, but something to look for when you're trying to create the desired reaction from the partial reactions. You can also multiply the partial reactions and add those together. Was that it? Hope this helps.